apologize, my phone isn't liking me very much tonight. It keeps shutting off in the middle of my videos. I am going to just pick up where I left off on that last video, looking at now evaluating logarithms and moving into some fractions and negatives. So something like log base 2 of 1/2. Well, log base 2 of 1/2, what power on 2 gives me 1/2 as an output, and that would be a -1. Remember, negative powers flip the base to the bottom, and so 2 to the -1 is equal to 1/2. That's the related exponential form. Okay. Another weird one is if you start with a base that's bigger than your argument. So what power on 9 gets you to 3? Well, if you think about that, 9 to what power would equal 3? Well, we know the square root of 9 is equal to 3, and a square root is really a 1/2 power. So because, that didn't show up very well in there, that's a half. Let's see, that should be a 1/2. No, that's still not showing up well. Let's just do it this way. Is that better? Yeah, that's better. That's clearly a 1/2. Okay, 9 to the 1/2 power is equal to 3. Because remember, 9 to the half power is the same as the square root of 9. And so the answer here is 1/2. Okay? Alright, and finally, just a simple conversion. Let's say you had an exponential, and maybe we didn't know the base, but we know everything else. We can convert this to the logarithmic form, and there's reasons why we may want to do this in the future, so practice it now. The base has to stay the base, right? Base of the exponential is the base of the log. The answer over here, the 72, is going to be your argument, and the power has to be the other side, or the answer to the logarithm. Okay? So these two things are interchangeable. Okay, so that gets us some practice with evaluating logarithms. Now, logarithms have some very interesting properties. In fact, I'm going to list out 10 properties that logarithms have. I'm going to briefly explain to you why they work the way they do without going into too much detail. I don't want the videos to get too long here. But there are going to be what I call 10, well, there are 10 properties that I'm going to point out, and I call them the 10 Commandments of Logarithms. Kind of a quirky name, but that's just what I like to call them. So this really bleeds into both sections 6.4 and 6.5 on properties of logs or logarithms. Okay, 6.4 and 6.5. And so, like I said, I call these the 10 Commandments of Logarithms. I can't claim to have originated that. I heard that from a colleague several years ago, and I adapted it, so now I run with it. But the 10 Commandments of Logarithms. Anyway, the first one, and really is the most fundamental and most important, is that original definition that we just looked at. Y equals log base a of x, which is equivalent to x equals a to the y. Alright, so these two things are interchangeable, and in fact this governs almost all of the other properties. For every logarithmic property there will be a corresponding exponential property, or property of exponents. Okay, so the second commandment of logarithms is this one, that the log base a of 1 is equal to something. If you input a 1 into a logarithm, the question is, what do you get out? And we actually saw it already with some of our other functions we already looked at. We looked at this a couple videos ago. Log base 2 of x, you input a 1, you get out a 0. It's the x-intercept of these graphs. And so it ends up being 0. Now why? Is it just because of the graph? Well, if you think about it in the other form here, a to the y, well, a to the 0, any number raised to the 0 is going to equal 1. There's a property, zero property of exponents that says that's true, so the corresponding logarithmic property is here. Number 3 also comes from a exponential property. Think about this one. If you had a to the 1 power, anything to the 1 is itself, right? And so if you turn that into a logarithmic expression, log base a of a is equal to 1. All right, so that's a basic one. Property number 4 is an interesting one. This one comes from the idea that a to any power is equal to itself, which seems kind of weird. But if you take the a to the power, if you take the a as your log base, the power here, we'll use the r. Oh, the power actually has to go to the other side. I'm doing this a little bit weird. So a is a, the x is this entire side, a to the r. So that's the input, and the answer is r. So if you think about it, what power takes a to the r? And the answer is r. Okay. This is also, interestingly, a composition of two inverses. And if you'll recall, we said when you have two inverse functions, their compositions will always equal x. Right? So if you input one function into the other, you'll always get the input out. Well, here I'm not using x, I'm using r, but it doesn't matter. If I take an exponential and insert it into a logarithm, I should get r. And vice versa for the composition. If I take a logarithm and insert it into an exponential, I should just get the original input out. Right? So my argument, my logarithm being inserted into the exponential just gives me the r value back out. Okay? Okay, so that's the fifth property, and that comes from the composition rather than from this exponent rule. Now, property number 6 is kind of an interesting one. Most of these are helping us to evaluate logarithms, but there are some logarithms that you actually can't evaluate, and that is the log base a of n when n is negative or 0. So this would be undefined if n is less than or equal to 0. And the reason for that also comes from these graphs we saw in the last couple videos and the domains. Remember, the domain for the logarithm is all positive numbers. And that was true for both the growth and for the decay. The domain was all positive numbers. And so you have to have positive numbers. I cannot input a negative or 0. It's just undefined. The graph isn't to the left of the y-axis. Property number 7 and number 8 and number 9 and number 10, actually all of these I'm going to put in the next video, so stay tuned.